Sorry, didn't see you there, driving my new sports car. You know what I love about sports cars is that there's so much science behind this. Motion, moving velocity, combustion engines. There's so much stuff that goes into a sports car that makes it, well, a sports car. But you guys don't want to hear about all that science stuff, not when you're on spring break. Wait, what? Spring break's over? Hello everyone and welcome back to Grade 10 Science. I'm your teacher, Mr.Drover, and I hope that everyone had a good spring break, or just a break in general, because it is snowing a lot here. So today, talking about science and cars and fast things that move, I think we better start our physics unit today. The main thing about physics, what everyone talks about, is motion. We all intuitively know what motion is. It's moving something from its position in space to somewhere else. But us scientists like to make things a little more complicated than that. In science, there's a particular type of motion that we always talk about that has different variables, adding math to it, which of course you add math to it because what science would not have math in it, right? But today we got to start our lesson with a type of motion that is rarely seen ever in nature because it's really hard to do by anything. That is called uniform motion. Uniform motion is motion with a constant speed that travels in a straight line. Let us use the example of me driving to the gym. In this example, the gym is exactly 10 kilometers away. Now imagine the road to the gym has no stops or yields and is a completely straight road, so no turning whatsoever. This means that I can travel at a constant 60 kilometers per hour the entire trip. Now, since we have both the total distance we traveled and the speed which we traveled at, we can find the total time. We simply go distance divided by speed. Our answer comes to a rounded 0.17. Now, since our units are in hours, this is actually 17% of 1 hour. And if we do a little more math, we can find out that 17% of an hour is approximately 10 minutes. So, like I said before, uniform motion is very hard to maintain. Even in that example, in the real world, you were still changing velocities a little bit. True uniform motion is very hard to come by. So instead of using uniform motion in our calculations, we tend to use average speed. This is what your GPS does at home. This is what pretty much every sort of GPS running watch does. It all uses average speed. Here, give me a second to park this thing and then I'll go into more detail. Okay, where were we? Uniform motion, that's correct. So, like I said, uniform motion is very hard to maintain in the real world, even in cruise control. So what we usually do is we calculate average speed instead. And this is where we get our first physics formula, all right? And that's average speed equals total distance over total time. So let's break down this formula. So the first variable we're dealing with is v, for velocity or speed, and we are going to use the units meters per second or kilometers per hour for that. The next variable is d, and that's going to be our distance, particularly our total distance in meters or kilometers. The next variable is going to be t for time, and that's going to be in seconds or hours depending on the question. And these all make up the formula v equals d over t, and that is the main formula we're going to be using for this unit. All right, now that I explained the basic formula, we can look at the PowerPoint and go through some examples together. All right, class, let's work through this example. So a baseball travels 20.0 meters in 1.5 seconds. Calculate the average speed. So the first thing you have to do here is identify your variables. 20.0 meters, that's the distance he travels. Now make sure to keep that decimal, even if it's a 0, because dealing with significant figures when we're looking at doing more than this, it's important. So we really want to keep all the significant figures. So don't just put 20, put 20.0, please. So if that is our distance, that means D will equal 20.0 meters. Remember to put the meters because you don't want to accidentally put kilometers instead, all right? So 1.5 seconds, calculate the average speed. So that would go under time. Time would be 1.5 seconds, okay? And then we're trying to find velocity, and we are not sure what that is, or speed, I should say. So we use our formula. Now, what did we just look at in our little animation there? Well, we know that V equals D over T, okay? So what we want to do now here is change the D over T into our actual numbers. So that's going to equal 20.0 meters divided by 1.50 seconds. All right, and now you can already tell the unit that this is going to come out as, because you have meters here and you have seconds here. So the unit will be meters per second. All right, so do some math for me. 20.0 divided 1.50 is going to equal 13.3 meters per second. All right. Okay, that example was with meters per second. Now let's expand that into a larger scale and do an example with kilometers. Okay, for this example, it says if a train traveled 100 kilometers in 0.500 hours, what is its speed in kilometers an hour and in meters per second? Okay, so the first thing we got to do is figure out what information we have. So let's look at 100 kilometers, that's the distance. 0.5 hours is the time, and we're trying to find the speed. So we rearrange our formula to exactly what we had before. V equals D over T. And that way we see 100 kilometers over 0.5 hours. We do the math there, and we are going to get 200 kilometers an hour, which makes sense because if you travel 100 kilometers in half an hour, if you maintain that speed, you're going to be traveling 200 kilometers in a full hour. Now, let's go here. How many minutes in an hour? In an hour. So 60 minutes an hour. How many seconds are in 1 minute? 60 seconds a minute. So how many meters in a kilometer is 1,000? So what we would do here is we'd go 200 kilometers times 1,000 meters a kilometer, and this is going to get how many meters we are going to be traveling. So, and then you would do that over 1 hour times 60 again in order to get the seconds. So what we're doing here is converting time from hours to seconds, and we're converting distance from kilometers to meters. So what this means is 200 times 1,000, that's 200,000 meters. But we're just going to put 200 kilometers here because we're going to look at the bottom number and we're going to see why. So if you go 60 times 60, you're going to get 3,600. So it's 3,600 seconds in in an hour. Wow, I have a bad cough. So if we divide that by 1,000, we get 3.6 here. So 200,000 meters divided by 3,600 seconds is going to get you 55.6 milliseconds. And it's important to keep that decimal for significant figure reasons. All right, let's move on. All right, hi guys. Sorry, my other camera cut out, so I'm gonna have to change the format a bit mid-lesson here, but I think we can still all do this pretty easy. Okay, so I have my document here. Let's go through example 3 again. Let's go through example 3, I mean. So how long would it take for a car to travel 4,000 meters if its speed was 40 meters per second? Okay, so again, what you want to do, even if it's written out like this on the PowerPoint, what I want you to do is go just list out your variables. Okay, so the distance equals 4,000 meters, and then the speed equals 40.0 meters per second. 0.0, sorry. Meters per second. 400. I'm sorry. So what you want to do here is you want to look at our equation. Our original equation was velocity equals distance over time. All right. Now that's all fine and dandy, but this is our first example where we are actually trying to find time instead. So what you want to do is you just want to rearrange it so it's time equal d over v. These all should be lowercase, I'm sorry. Even this would be. Okay. So we rearranged our formula. And to do that, basically what I do is I just throw the t over the equal sign, and what happens when you throw it over the equal sign, it changes from a multiplication to a division. So or a division to multiplication. So since it was divided by t now, it's going to be just t there, and then you're going to throw the v over, and since the v was multiplication, it's going to turn into division, so distance over time. All right. And then basically what we do is we put in our formula here. So we go t equals 4,000 divided by velocity, which is 40.0. And t equals, you guessed it, 100 seconds. Okay. Now, the main thing is this was nice and easy because the distance was in meters and the speed was in milliseconds, meters per seconds, I'm sorry. So make sure that, so if that was 4 kilometers, you would have to change that or else it wouldn't be correct because the units have to match. Meters have to match with meters, okay? So let's move on to our next example, okay? So example 4 here. So how far does a motorist travel if he's moving at a speed of 26.5 meters per second for 4 hours and 15 minutes? Okay, so this is getting tricky here. This is why we need to look at our variables and isolate everything. So we got our v, okay? So our v equals 26.5 meters per second. We have our time too. Time is 4 hours and 15 minutes. Okay, but what we need to do now is we need to change this time from hours and minutes to just seconds. So the first thing I would do is I'd figure out how many minutes is in 4 hours. So if you had 4 times 60, you would get minutes. You get the minutes in 4 hours, but if you times it by 60 again, you'll get how many seconds is in that. So let's pull out the calculator here. Four times 60 times 60. So in 4 hours, there is 14,400 seconds. Okay? Plus the 15 minutes. So that would be 60 times 15. All right? So if we keep doing that, we go 1440s plus 900 seconds. Our total time will equal 15,300 seconds. So 15,300 seconds. This is important to do, guys. Okay, please make sure you do it. So now that we got that all the way, wow. So now that we have that out of the way, we can just do rearrange the formula once again. So since we have time and we have velocity, you're going to be distance equals v times t, okay? So distance equals velocity, which is 26.5 times 15,300, 15,300, and you are going to get a giant, sorry, force habit. You're going to get a giant number here. So, that is going to be 26.5 times 15,300. You're going to get 403,450. Now, this is where scientific notation comes in, because we want to do that here. So the rules of scientific notation is we have to lower it down to a number between 1 and 9. So we can go distance equals 40 is bigger than 9, so it has to be 45. So 4.05 times, how many times did we move the decimal point? 1, 2, 3, 4, 5. So 10 to the power of 5 meters. Or you could write 405 kilometers, right? So those are the examples in terms of figuring out distance, velocity, and time, or speed, I should say. Let's carry on to graphing. All right, everyone, before I start moving forward here, I just want to give you a tidbit of advice. So when I'm talking here, please pause the video and write down stuff, all right? Especially when we're talking about graphing, please follow along, but follow along in a way where you're pausing, you're drawing out the graphs, because drawing out the graphs are going to help you remember a lot more than just looking at the video, okay? So please pause the video, draw along, and if I'm moving too fast, just pause. That's all you have to do, all right? But without further ado, let's just jump into it. So with meters per second and distance and time, we all want to figure out where we're going and how fast we're getting there. There's a sweet way of visualizing this. So throwing back to grade, 8 math, talking about graphing. We're going to discuss how to create a graph here. So the things you need here is a ruler and a pencil. If you don't have a ruler, any straight edge you have is fine, but please have it straight. It makes a whole lot of difference, okay? So again, the first thing you do when you're answering a question is actually the same thing you do when you're creating a graph. You got to identify your variables, okay? This is the most important thing, and this is why people get messed up in word problems during math all the time, because they don't identify the variables. So identify your variables. Identify what's the distance, what's the time, what's the speed, and which one you have to find out of those three, okay? Place the manipulated variable on the x-axis. So the x-axis is the horizontal line, which means like it's the ground line, okay? And so side to side. And then in physics, it's always used for time. Label it and include the units. So it's important to label your graph, okay? The next step would place the responding variable on the y-axis. So that's the vertical line that's going up and down, okay? In physics, this may be distance, displacement, speed, velocity, acceleration. Whichever one it is, label it and include the units. Again, meters per second or meters, kilometers. It has to be a particular unit, okay? And then use a scale that fits the data given. So when you label the data, so you label when you label the graph, you have to point little numeric values on the up and down side to side. Now, if you're dealing with something that's going up to the speed of like 100 kilometers an hour, and you're trying to calculate speed, you don't want to put 1 kilometer an hour every time, or else that's just going to go past the graph. So make sure it fits your data, okay? So another thing is that once you pick the scale, don't change the scale. So if you're going up by 2s, stick by going up by 2s. Don't go up by 2s for half of it, then up by 1 for 1. Don't do that, okay? Terrible idea. Again, there should be no big jumps on the number line. Okay? So plot your data points from this chart given. Create a line of best fit. So this should be one solid line, not connecting the dots. Okay? You do not place an arrow at the end of the line, as you are simply being asked to plot the data and not given an extrapolation. So don't put an arrow on it, because that means that you're predicting what else could be after the fact. We're just writing down the data we have. So don't put the arrow on it. We're just showing what we have. We're not predicting anything. Give the graph a title. So distance as a function of time would be a smart one to do if you're trying to find distance. If your variable speed as a function of time. Okay. So when speed is constant, distance varies directly with time. So when we're dealing with uniform motion, where the speed doesn't change at all, the line is going to be straight. It's going to be linear. Okay. This can be represented on a graph with the time on the x-axis and the distance on the y-axis. So looking at this, so this is the graph I was talking about. So if you're confused with what I was talking about earlier, look at this now. Okay. So you plot it. So this is going distance upwards by 20 meters. So 20, 40, 60, 80, 100. Notice how he doesn't change it. It's the same scale all the way up. For his time, he goes 1, 2, 3, 4, 5 in seconds. Okay. There's no line. There's no arrow there. So we're just plotting the data points. So time. So 0, 0. Because no matter how fast he's going, at time 0, you're going to start at 0 distance. The next spot would be 1 second. 1 second, he travels 20 meters. 20 meters. The next second, he travels another 20 meters. So the total is 40. And it goes up and up and up. Now, I bet from just looking at this graph that you're totally able to understand how fast this guy is going. Meters per second anyway. But let's do it here. So slope of the graph is the steepness. So this is a pretty 45-degree angle. It's not too steep, but it's not that flat anyway. But we're just trying to figure out the slope, and the slope is how much things are changing over time, right? So slope is equal to rise over run. And that's calculated. The rise is how much it goes up, and then the x is how much it goes down. All right. So, the x is the run, how much it's going to the right. Okay. So the way you do that is you go y2 minus y1, and you're wondering what y2 is. Well, if you look at it, y2 is the last point on the graph that we have. So that would be y2. Y1 would be 0. X2 is the farthest point on the graph on the x-axis. So that's 5 for us. and then x1 would be the start of the x-axis, which is 0. So if we put this into our formula here, rise over run is 100 meters minus 100 meters. So 100 meters minus 100 meters divided by 5 seconds minus 0 seconds. So it's basically 100 meters divided by 5 seconds. So notice how you have the meters on top and the seconds on the bottom. That gives away what unit is going to be your final answer, which is meters per second. So 100 divided by 5 is 20. So the slope is 20 meters per second. And you can tell that because every second it goes 20 meters farther. All right. So just to tell you more, the slope of a distance time graph is the speed of an object. So every time you hear slope regarding a distance and time graph, you're going to be getting the speed of the object. So if you got the slope, it's technically the speed. The steeper the slope of a distance time graph, the higher the rate of speed. So again, the steeper this is, the faster it's going upwards compared to how it's going horizontally. So of course it's going to be a bit faster. Moving on. What I was just talking about in terms of distance time graph here, you have you have the slower, this way, right? The slower one, that's less steep, okay? Then you have the one that we just worked with, which is right there-ish, okay? And that one's in the middle. It's about as steep as we just looked at in our example. And then if you go up to the top one, the one that's labeled fast, that means that it's going a lot of distance in not a lot of time. All right. So now that was distance time graphs. Now we're going to look at speed time graphs, okay? Now we can plot the graph speed versus time the same way we plot distance versus time. So look at this example right here. We have a little chart here that shows at time 0 we are moving 5 meters per second. Okay, at time 2 seconds we are moving 5 meters per second. Time 4 seconds we are moving 5 meters per second, and then so on. It's always 5 meters. So what this means is speed doesn't change whatsoever during the time. So again, we're not looking at distance here. We're just calculating the change in speed. Okay, the speed going lower or farther, lower or higher. So the slope of the graph is 0, which indicates that the motion is uniform. Again, this is a straight line here. If you look at it, it's just a straight line. That means there's no changes. It's flatlined. So the slope of the graph is 0. So it doesn't go up or down or anything like that. So the slope is 0. So this tells you that the speed is constant, okay? It doesn't tell you that there's no speed. It just tells you that it's constant, okay? It's constantly 5 meters per second. The slope of the graph is 0. Any other slope would indicate non-uniform motion, which means the object speed is changing as time passes. So again, for most things in life, this thing would vary, but for uniform motion, it doesn't. So an upward slope, if you saw an upward slope going upwards, the speed would be increasing. If it went downwards, the slope would be decreasing. The area under a speed time graph is the distance traveled by the object. So you could have it length times width or half base times height, either way. But the area under the speed graph is the distance traveled by the object. So if you went 5 times 10, right? Length times width, then you would get 50 meters. Which makes sense because he was traveling 5 times 10. Okay. So calculate the area under the following speed time graph up to 10 seconds. So we just did this, right? Length times width. Length is 10 seconds. the width is 5.0 meters per second equals 50 meters per second. All right. So that's how you do graphs. All right, so that is the end of today's lecture. If you have any questions, please contact me or write it down in the Google Classroom chat. I will get back to you as soon as I can. You have assignment today. It's 4 pages that have a couple questions each on them, and it's all about converting units and trying to find distance, speed, or time using the PowerPoint and the lesson that I just taught. All right. So go through this with your PowerPoint open and the video open and see if you can do all this. All right. Nothing here is particularly crazy in terms of difficulty. If you just read your textbook and you read the PowerPoint and you listen to my video, I am fairly certain everyone can do this. But again, if you have questions, please let me know. All right. So I have this. I will link it into the Google Classroom, and you guys have all week to work on this. All right. See you guys next week.